This is Chapter 16, A Universe of Galaxies for Astronomy 100. In this chapter we're going to look at islands of stars, the distances of the galaxies, galaxy evolution, and active galactic nuclei. So in the first section, let's look at islands of stars. Our goals are to find out what the three major types of galaxies are and to see how galaxies are grouped together. Here's a Hubble Deep Field Telescope view of a bunch of galaxies. They show a great variety of galaxies, some of them billions of light years away. A galaxy's age, its distance, and the age of the universe are all closely related. The study of galaxies is connected with the science of cosmology. That's the study of the structure and evolution of the universe. So let's see what the three types of galaxies are. Here's a Hubble Deep Field Telescope view, and down in the lower right you can see what appears to be a fuzzy splotch of light. It actually turns out to be a very large spiral galaxy. Here's another blob of light. If we look at it more closely, we see that it's an elliptical galaxy. And down in the lower left, we see another blob of what appears to be kind of a yellowish and bluish light. That's an irregular galaxy, or at least two, possibly three irregular galaxies, all within the same photograph. We've already studied spiral galaxies. We know that they consist of billions of stars. We have a disk, which is kind of a flat-shaped circular structure. We have a bulge at the middle. We have a halo of stars around a spherical cloud around the galaxy. And within the halo we have globular clusters. The components are all about the same here, with many gas clouds obviously. You see the halo, you see the arms, but it has more of a spheroidal component. In other words, very few gas clouds, so very few new stars are forming. So in this sort of top-down view, we have the disk component and the spheroidal component. So this is, with the spiral arms, classified as a spiral galaxy. The blue-white color indicates ongoing star formation, and the reddish-yellow colors indicates older stars. This is a little bit different from our spiral galaxy, the Milky Way. It's called a barred spiral. Instead of a spheroidal type of bulge, it has more of an oval or a football shaped. So it's called a barred spiral galaxy. Here's a lenticular galaxy. It has a disk like a spiral galaxy, but it's much less dusty. So we have definitely something here which is a finite bulge. Here's an elliptical galaxy. It's all spheroidal in its structure, virtually no disk. And the reddish-yellow color indicates older stars. Here's an irregular galaxy. Irregular galaxies can be any shape or size. They're neither spiral nor elliptical, but the blue-white color indicates newer stars. So scientists by the name of Hubble came up with a star, or I should say galaxy classification system. This is not how a galaxy evolves, this is just how the classification system works. Starting over on the right, we have spiral galaxies, then they become more and more elliptical as we go toward the left, rounder, as it says in the picture here. So this classification system has been used quite a bit for classifying galaxies. This is the same as what you see on page 408 of the textbook. So how are galaxies grouped together? Well, spiral galaxies are often found in groups of galaxies, up to a few dozen galaxies per group. So that's one classification. And then elliptical galaxies are much more common in clusters of galaxies, where you have hundreds or thousands of galaxies. So that's where you'll find ellipticals. So what are the three major types of galaxies? Well, they're the spiral, the elliptical, and the irregular. Spirals have both disk and spheroidal components. Ellipticals have no disk. They're just spheroidal. And then how are they grouped together? Now, spiral galaxies tend to collect into groups of a few dozen galaxies. Elliptical galaxies are more common in large clusters containing hundreds to thousands of galaxies. Just remember, though, as we're talking about galaxies, these are groups of stars that contain millions or billions of stars. So in this next section, let's look at the distances of galaxies. How do we measure their distances? What's something called the Hubble's law? And how do distance measurements tell us the age of the universe? Well, this is our yardstick or meter stick for measuring distances to objects out in space. We'll go through each of these. It's fairly easy to find the distance to an object fairly close within our solar system, such as the moon or Venus or maybe even Mercury. We can use radar, which is a radio wave bounced off an object and the reflection sent back. Us being able to time it, we come up with the actual distance to that object. We've looked at parallax in the past, where measuring or being able to measure the angle against a group of more distant stars, the change in its position relative to those stars between, let's say, 2 days in the year, we can come up with distances out to a few hundred light years. Now, I know we've covered this before, but again, there's this relationship between the brightness and the luminosity of an object. The luminosity is the actual brightness of the star, whereas the brightness is dependent on how far away we are from that star. And of course, if we know one or the other, we can figure out the distance to that star. So that's called a standard candle. It's an object whose luminosity we can determine without measuring its distance. Now here's another way we can measure distances. The apparent brightness of a star cluster's main sequence tells us its distance. If we know what one main sequence of stars is, and we can look at this other main sequence of stars, being able to see that they're brighter or dimmer, we can calculate their approximate distance. So knowing a star cluster's distance, we can determine the luminosity of each type of star within it. We know Cepheid variable stars are very, very luminous. As you can see in the HR diagram here, variable stars with periods of hours called RR Lyrae variables. And we have these things called Cepheid variables with periods of a few days. So depending on where they are, or depending on their brightness, we know what their luminosity is. We can determine how far away they are. Here's a diagram of Cepheid variable stars' brightness as it changes. The brightness peaks every 50 days in this case. So it rises and falls over a 50-day period. That's called a Cepheid variable. If we graph that relationship between luminosity and period, it comes up with a fairly straight line. So knowing the period of the variable star, we have some clue as to its luminosity. And if we can find its luminosity, we can determine its distance. Here's a white dwarf supernova that can also be used as a standard candle. How about the apparent brightness of a white dwarf supernova, telling us the distance to its galaxy, in this case up to 10 billion years. Again, we know what a white dwarf is like. We know what its luminosity is. So based on what its brightness appears to be, we come up with the distance. Here's something called a spiral nebula. Before Hubble came around, some scientists argued that spiral nebulae were giant galaxies, like our Milky Way, but other scientists thought that they were smaller collections of stars within our own Milky Way. So the debate remained unsettled until someone finally measured the distances to these spiral nebulae. He settled the debate by measuring the distance to the Andromeda galaxy with Cepheid variables in it, using those as standard candles and actually measuring or approximating the distance to the Andromeda galaxy. He came up with this idea that these stars, although similar, and of course the galaxy itself, showed a redshift. In other words, by Doppler shift, it was easy for him to see that there was a 5% shift in the light based on the wavelengths of energy that were being received from that galaxy. He measured distances to other galaxies, and he found that the relationship between the redshift and the distance were related. As you can see in the bottom left of this animation, those red dots form a fairly straight line. So there's apparently this relationship between the Doppler shift and the distance that object or that galaxy is away from us. So he came up with something called Hubble's law, that there's a relationship between the speed or the recessional velocity a galaxy has and distance. And of course he had to come up with this figure called Hubble's constant, which is h sub 0 down along the bottom. So if he could find the recessional velocity of a galaxy and then do a calculation on that with his constant, he could actually find the distance to that galaxy. So as you can see, if we know the recessional velocity, we can go up along the vertical axis, draw a straight line across to the red line, and then drop a line vertically down and find out the apparent distance. So the redshift of a galaxy tells us its distance through Hubble's law. Velocity over Hubble's constant gives us the approximate distance to that galaxy. So distances to the farthest galaxies can now be measured by using the redshift of the galaxy. Since most galaxies are receding from us, they're redshifting. So as we saw at the beginning of this section, these are all different ways that we can measure distances in space. Radar, parallax, main sequence fitting, Cepheid variables, and by using Hubble's law. So how do distance measurements tell us the age of the universe? This is the graph we looked at before. Well, Hubble's constant tells us the age of the universe because it relates velocities and distances of all the galaxies. Remember, distance over velocity can actually give us the age of that galaxy away from us. And of course, the farther out we can measure those recessional velocities, the older the galaxy will probably be. So the expansion rate seems to be the same everywhere in space. In other words, the universe has no center and no edge, at least as far as we can tell right now. This is a good analogy to recall the fact that if we have these 4 dots, A, B, C, and D on this balloon, and we expand the balloon, in other words, we blow it up a little bit, the distances away from each of those dots it will increase no matter which dot we're on. So, the universe looks about the same no matter where you are within it. Matter seems to be evenly distributed. There's no center, there's no edges, but it's not proved, but it's consistent with all the observations scientists have made up to now. So we're fairly certain that this is the case. So the distances between faraway galaxies change while light travels, obviously. If a galaxy is moving away from us, then the farther out it is, the longer those wavelengths are. Astronomers like to think of this in terms of what they call look-back time rather than distance. Yes, it is a distance, but it's also a time, since we know the relationship between recessional velocity and their actual distance. So it's another way of looking at what we see in terms of galaxies moving away from us. They're moving away, but we're also looking back in time. So expansion stretches the photon wavelengths, causing a cosmological redshift directly related to the look-back time. So in other words, if we have an object out there such as a galaxy with such and such a wavelength redshifting, we can actually estimate how far back that galaxy originally formed. So what have we learned? Well, the distance measurement chain begins with parallax measurements, they build on radar, and so on and so on. Using parallax and relationship between luminosity, distance, and brightness, we can actually come up with a series of standard candles. And we can measure distances greater than 10 billion light years using white dwarf supernovae as standard candles. So what is Hubble's law? Well, again, we've already looked at this. It's telling us that as a galaxy is redshifting from us, there's a relationship between that recessional velocity and the actual distance to the galaxy. How do distance measurements tell us the age of the universe? Well, measuring a galaxy's distance and speed allows us to figure out how long ago the galaxy reached that distance. And measuring Hubble's constant tells us that that amount of time is roughly 14 billion years. So in this last section, let's look at how we study galaxy evolution and how or why do galaxies differ. This is a series of pictures in your book that gives you an approximate age of these various types of galaxies. So deep observations show us very distant galaxies that were formed much earlier in time, old light from young galaxies, basically. We can model galaxy formation. I mean, the matter originally filled all of space pretty uniformly, and the gravity of the denser regions pulled in the surrounding matter. That just makes sense, that gravity pulling these protogalactic clouds together would be the places where galaxies would first form. So the denser regions contracted, forming these huge protogalactic clouds. Hydrogen and helium gases in those clouds formed the first stars. Supernova explosions from those first stars kept much of the gas from forming, but leftover gas settled into a spinning disk. And as you recall earlier in this course, we talked about the conservation of angular momentum. So that's what's been happening here to cause the galaxy to spin up. But here's a couple of galaxies that obviously look very different. We have a spiral galaxy on the left and some sort of elliptical galaxy on the right. So why do these galaxies differ? Well, apparently the density of the cloud helped determine whether it would be spiral or elliptical. Why don't they all have similar disks as we see in Hubble's diagram? Why aren't all of these the same? Well, maybe that had to do with the spin, the amount of angular momentum that the disk or the cloud had initially could have resulted in different shapes of the disk. The density of the cloud may have made a difference too. Able to cool and form the stars before the gas settled into the disk. The higher densities would form one type of galaxy versus the lower density galaxies. We have distant red ellipticals, showing observations of some of these support the idea that most of their stars formed very early in the history of the universe, as you see on page 422. And I think one of the more interesting parts of this chapter has to do with collisions of galaxies. That's certainly a possibility. Collisions were much more likely early in time because they were closer together. So we can actually assume that some galaxies collided, and the type of galaxies that collided may have formed a new kind of galaxy. Many of the galaxies we see at great distances look violently disturbed. As you can see here, they appear to be some very strange, irregular galaxies. The conditions we observe nearby trigger bursts of star formations too. So a collision may have actually caused stars to form. We can actually take the physics of galaxies colliding and put them into a computer simulation. And in this case, we see two spiral galaxies merging into an elliptical galaxy. Collisions might explain why elliptical galaxies tend to be found where galaxies are closer together. Maybe they are the result of those collisions. Giant elliptical galaxies at the centers of clusters seem to have consumed a number of smaller galaxies. So it just kind of makes sense that more galaxy collisions would form a larger galaxy. Here's a starburst galaxy, forming stars so quickly they'll probably use up their gas in less than 1 billion years. As you can see, the bluish area there would be the region where the newer stars, the shorter lived stars, would actually form. The intensity of those explosions could drive galactic winds, blowing gas and dust out into space. So how do we study galaxy evolution? Well, deep observations of the universe are showing us the history of galaxies because we're seeing galaxies as they were at different ages. Remember, the farther out you look, the older the galaxy is. And we use computer modeling to match theory with observation, such as with galaxy collisions. Why do they differ? Well, some of the differences between galaxies may arise from the conditions in their protogalactic clouds, and collisions may have also played a major role in transforming spiral galaxies into elliptical galaxies. So what's the evidence for supermassive black holes at the centers of our galaxy? And why do we think the growth of central black holes is related to galaxy evolution? What's the evidence for supermassive black holes at the centers of galaxies? As you can see here, there apparently is an active galactic nucleus with a huge jet of particles flying out from in that one particular direction. If the center of a galaxy is unusually bright, we call it an active galactic nucleus. And the most luminous of these is called a quasar. Quasar is short for quasi-stellar radio source. We have some highly redshifted spectra of quasars, so they must be very, very far out in space. We find the luminosities of those stars, though, are huge. 10 to the 6th would be 1,000,000, 10 to the 9th would be 1,000,000,000, 10 to the 12th would be 1,000,000,000,000 suns. So the quasar could have a mass or a luminosity greater than 10 billion suns. The variability shows that all this energy comes from a region smaller than the solar system, though, so it must be one huge, massive star. This is an interesting thought question. What do you conclude from the fact that quasars usually have very large redshifts? Well, the first one is easy. They're generally very distant. If they're very distant, they were possibly more common early in time because that was the initial version of a star or a galaxy. Galaxy collisions might actually activate them, and nearby galaxies might actually hold dead quasars. In other words, stars that were that luminous but have long died out. Galaxies around quasars sometimes appear disturbed by collisions, as we see here. There's some sort of galaxy around this quasar that has a very odd shape. Quasars will radiate energy over a very wide range of wavelengths, indicating that matter within it has a wide range of temperatures. So we have this phenomenon where this extremely bright light is also able to emit a lot of different wavelengths of energy. These are radio galaxies. They contain active nuclei shooting out jets of plasma. They emit radio waves, and they come from electrons moving at nearly the speed of light. So we have actual evidence of what we call radio galaxies. Basically, something that would only be visible by looking at them through a radio telescope. Here's lobes of radio galaxies extending out into space, possibly hundreds of millions of light years out. An active galactic nucleus can shoot out blobs of plasma at almost the speed of light, and the speed of ejection suggests that a black hole might be responsible for it. Radio galaxies don't appear as quasars because dusty gas clouds block our view of their accretion disks. So we're thinking they're not the same object. So, characteristics of an active galaxy. Luminosities must be huge. Luminosity can vary rapidly. They emit energy over a wide range of wavelengths, and some actually have jets of plasma shooting out at nearly the speed of light. So the accretion of gas into a supermassive black hole appears to be the only way to explain the properties of quasars. Jets are thought to come from the twisting of the magnetic field as part of the accretion disk. So why do we think the growth of a central black hole is related to galaxy evolution? Well, remember we've seen this picture before, where orbits of stars at the center of our Milky Way indicate there's a very, very large black hole in the center. The orbital speed and the distance of the gas orbiting the center indicates there's a black hole there with a mass of at least 3 billion suns. So many nearby galaxies, maybe all of them, have supermassive black holes. The black holes seem to be dormant, active galactic nuclei. And all galaxies may have passed through this quasar-like stage earlier in time. So the evolution of a galaxy to a point where we see it today may have actually involved a quasar at the center of that galaxy. Now it's a black hole. So the mass of a galaxy's central black hole is closely related to the mass of the bulge. As you can see by the graph here, that's a pretty straight line based on the white dots that you see there. There appears to be a definite relationship there between the bulge and the black hole mass. The larger the bulge, the larger the black hole. The development of a central black hole must somehow be related to galaxy evolution. So here, what's the evidence for supermassive black holes? Well, we have active galactic nuclei, very bright objects, and the only model that explains it so far is that supermassive black holes are the power source. Why do we think the growth of black holes is related to galaxy evolution? Well, observations of stars and gas clouds orbiting the centers of galaxies indicate that many galaxies have, perhaps, supermassive black holes in the center. And the masses of those black holes are very closely related to the properties of their home galaxy, in other words, the bulge, suggesting a connection between the black hole and how the galaxy evolved.